Hi dear students, today let's discuss about the magnetic effect of electric current part 3. Okay, so we have learned that an electric current flowing through a conductor produces a magnetic field, right? So far now we have discussed about that, like conductor carrying current, they produces a magnetic field. Do you know that the field also exerts a equivalent opposite force on the current carrying conductor? Cleared? Okay, not only the conductor exerts a force, but magnet also exerts equivalent opposite force. Yes, so this is suggested by the scientist, French scientist Andre Marie Ampere. Yes, the force due to a magnetic field acting on a current carrying conductor, it can be demonstrated through a following activity. That is activity 13.7. Take a small aluminium rod AB of about 5 cm using two connecting wires, suspend it horizontally from a stand. Okay, place a strong horseshoe magnet in such a way that the rod lies between the two poles with the magnetic field directed upwards. For this, put the north pole of the magnet vertically below and south pole vertically above the aluminium rod. Now, connect the aluminium rod in series with a battery and a key. So pass the current through aluminium rod from end B to end A. Observe it. Yes. What do you observe? It is observed that the rod is displaced towards the left. You will notice that the rod gets displaced and it displays towards the left side. Now, reverse the direction of the current flowing through the rod. That is current from A to B. Yes. What did you see? Rod is displaced towards its right side, right? Yes, it is now towards the right. Why does the rod gets displaced? Because of the current, right? And also when you change the direction, the rod, the direction of the displacement also changed. Okay, now change the magnetic field, okay, the poles of the magnetic field. That is, north pole is above the rod and south is below the rod. Let's see what happens. See the rod AB, okay, how it moves. Yes, again there is a displacement, right? Rod displaced towards the left. That is, when we change the magnetic field, the rod gets displaced. So we can conclude that there is a displacement of rod when the change in direction of the current as well as change in the direction of the magnetic field. Now keep the current and magnetic field, that is magnet, perpendicular to each other, that is at right angle. See the direction of the current and the magnetic field. So they are perpendicular to each other, right? And see the position of the rod. It is also at right 90 degree, right? And more displacement occurs in this case. Cleared? So we considered the direction of the current and that of magnetic field perpendicular to each other and found that The force is perpendicular to both of them. You see the rod, then magnet, then the current, direction of the current. So both are perpendicular to each other. So the three directions can be illustrated through a simple rule called Fleming's left hand rule. Okay, Fleming's left hand rule. This rule says that stretch the thumb, forefinger and middle finger of your left hand such that they are mutually perpendicular. If the first finger, that is forefinger, indicates the magnetic field, direction of magnetic field, and the second finger, that is the middle finger, indicates the current, direction of the current, then the thumb will point in the direction of motion or the force acting on the conductor. Okay, so these three fingers indicates the direction of the current, then the direction of the magnetic field and the direction of the conductor, that is the rod AB, and these are perpendicular to each other. And devices that use current carrying conductors and magnetic field include electric motor, then generator, loudspeakers, microphones and measuring instruments. Yes. Okay, so this is about the force on current carrying conductor in a magnetic field. Okay, through this activity we can infer that magnetic field, magnet also exerts equal and opposite force on a conductor. Okay, so some of the devices works using this principle. So let us discuss about the electric motor that works on the same principle. Okay, let's discuss about the electric motor. So what is electric motor? You all are familiar with this motor, right? You will do the project using these motors, small motors. So it is a rotating device which converts electrical energy into mechanical energy. Okay, and this electric motor works on the principle that a current carrying conductor placed in a magnetic field experiences a force, that is Fleming's left hand rule. Okay, remember that. Now let's see the construction of this DC motor. So DC motor consists of an insulated copper coil of many turns wound over a soft iron core. In the figure ABCD represents the coils. Okay, the ABCD is a coil. Then the coil is placed between the pole piece of concave cylindrical magnet. So it is placed between north and south pole of the magnet. And the free ends of the copper wire. Here you can see the these two ends, and these two ends are connected to the two half rings of a copper. Here you can see the split rings. It is also called as split rings. These free ends are connected to the split rings. Okay. Then the two carbon brushes touch the rings. The brushes are connected to the battery. Then these two brushes, carbon brushes, okay, they connected to the battery. Okay, now let's discuss the parts of this motor. First one is what? Field magnet. Okay, field magnet is a strong horseshoe type magnet with the concave poles. Then the second one is armature, that is rectangular coil ABCD, having a large number of turns of thin insulated copper wire wound over soft iron coil, that is called armature. Then the split rings, it is also called as a commutator. It is a cylindrical metal ring split into two halves. Then the brushes, it is made of graphite. It maintains a sliding contact with the split rings. Okay, so what is the function of split ring in the motor? Yes, it reverses the direction of the current in the coil after every half rotation. Remember that. What is the function of split ring? It changes the direction of the current. Then now let's see the working of DC motor, how it works through the video. Okay, understand the working of DC motor through this video, and this is important part.
When I turn on this switch, an electric current starts running and our fan spins. Such devices which convert electricity into rotation, we give a name to it, we call it the electric motor. And these devices are used in many places, like in your washing machines, your drilling machines, or even your electric cars. But the big question is, how does an electric current, which is basically moving electrons, push something as big as a fan and make it spin? The secret to these motors are magnets. In a previous video, we had seen that a current carrying wire can be pushed by magnets, or more technically, magnetic fields. So an electric motor uses this magnetic push to spin a current carrying conductor. So in this video, let's explore exactly how it works. So let's start with a couple of magnets, which will generate a magnetic field that's going to push our current carrying wire. And instead of just introducing a single wire carrying current, we will introduce a current carrying rectangular loop. Now the loop can be of any shape, but if you take it as a rectangle, it'll be easier to analyze this. And if you're wondering why are we considering a loop, we'll soon understand why. And as of now, let's not worry about where the current is coming from, where the battery is. We'll deal with that later. Now, each side of this rectangular loop is a current carrying wire inside a magnetic field. That means each side will experience a force. And as a result, this coil might start moving. Now, to figure out how this coil will move, we need to figure out the direction of the force acting on each side of this loop. And to do that, we have seen before, we can use the left hand rule, where you take your left hand, you stretch your fingers like this, and remember FBI, the thumb gives the direction of the force, the forefinger gives magnetic field, and the middle finger gives us the direction of the current. So to figure out the force on any side of the wire, we just have to align our fingers in according to the current and the magnetic field, and the thumb will tell us what direction the force is. And so what we need to do next is apply this left hand rule to each side of the wire. And so, can you try and do this yourself first? So, great idea to pause the video and see if you can apply this yourself and figure out the direction of the force. Alright, let's do this. Let's start with the pink wire. The current is inwards and the magnetic field is to the left. So, if we align our left hand, it will look somewhat like this. And so notice the thumb is pointing upwards, and as a result, the force is upwards. Now, if we apply the same left hand rule to this side, we see that the force is acting downwards. And if you look at these two remaining sides, the current is parallel to the magnetic field. And we've seen before, whenever our electric current is parallel to the magnetic field, the field does not push it. And so there will be no forces acting on this wire or on this wire. So there will be an upward force here and a downward force over here. And as a result, our coil will start moving. But how exactly will it move now? Well, here's my board. Let's imagine this is our rectangular coil. Notice on the left side I'm going to push it up, on the right side I'm going to push it down, and as a result, notice it starts spinning. So just like this, our coil will also start spinning. And in fact, over here, it's going to spin in the clockwise direction. So the same thing will happen over here. Our coil will start spinning in the clockwise direction. Now, as it spins, the forces on this wire and this wire will remain the same, because the magnetic field is still in the same direction, The current is still into the screen over here. That has not changed. So the force over here will still be up, and the force over here will still be down. But if you're curious, you may wonder what happens now to the forces on this side and this side. Earlier, they were parallel to the magnetic field, but now they are no longer parallel to the magnetic field. So, won't there be forces acting on these wires now as well? Yes, there will be. Won't those forces affect our rotation? No, they won't. Why not? Let's see why. Well, if we apply the left-hand rule to this wire, notice the magnetic field is to the left. The current is sort of downwards. So if you apply the left-hand rule, we see that the force will be into the screen. Now similarly, if we apply the left-hand rule on this side, over here the force comes out of the screen. So there are forces acting on these wires, but what are these forces doing? They're just pulling this coil apart. It's just like taking this board and pulling it like this. These two forces are not going to do anything. They're just going to cancel out. They're not going to provide any rotation. And as a result, we can totally ignore these forces. They will not affect our rotation at all. So throughout the entire rotation, we will ignore the forces acting on this side and this side because they're just going to cancel out. They will not affect our rotation. So yay, our coil is now spinning. But pretty soon we run into a problem. You see, if we bring back our board, if we want this board to continuously keep spinning in the clockwise direction, let's say, then notice the force on the right must always be down and the force on the left must always be up. It should always follow that rule. Over here, once the pink wire comes to the right, notice the force on the right side has become up and the force on the left side has become down. This will spin my coil back in the anti-clockwise direction. So you know what's going to happen next? Next, my coil will spin back like this. Now again, the coil will spin forward in the clockwise, anti-clockwise, clockwise, anti-clockwise. This is bad. This is not a motor, or at least not a good motor, because it's not completing even a single rotation. So how do we fix this? Well, to make sure it continuously keeps spinning in the clockwise direction, we have to somehow make sure when this position comes, the force on this wire should become downwards and the force on this wire should become upwards, right? Only then it will continue spinning in the clockwise direction. So we need to reverse the direction of the forces. But the question is, how do we do that? Well, again, let's bring in our left hand. So to reverse the force, say over here, we want the thumb to point downwards. Now there are two ways to do that. One, we can reverse the forefinger, that is the magnetic field, keeping the current same. That's one way to do that. But we'll not do that because flipping the direction of the magnetic field is not all that easy. We have to change the poles and we cannot do that automatically. But another way in which we can achieve this is we can keep the magnetic field the same direction, but we can reverse the direction of our middle finger, our current, like this. And as a result, our force will now point downwards over here. So if we flip the direction of the current everywhere, then the force direction will change everywhere. So the force over here will be downwards and the force over here will be upwards. And if you're wondering, well, how can we change the direction of the current just like that? We'll see how to do that a little bit later. But that's the most important thing over here. In this position, we have to change the direction of the current. So let's get rid of our hand, flip the direction of the current, and now the forces flip, and as a result, our coil will continue to spin in the clockwise direction. Yay! This will happen until, again, once the blue wire flips over. Now once the blue wire comes to the right and the pink wire comes to the left, again we have the same problem. Now again on the right hand side the force is up, left hand side the force is down. And again, we need to do the same thing. We need to change the direction of the current. Here it is, change. Once we change the direction of the current, the coil will continue to spin. And so by changing the direction of the current, every half a rotation, the direction of the forces will change and our coil will continuously keep spinning. Finally, we have converted electricity into rotation. Now, of course, in this animation, I'm pausing every time the current is changing so that we can see the forces flipping. But of course, in reality, the thing will keep on spinning continuously. The last thing we need to explore is how do we attach a battery to this and make sure that the current direction reverses after every half a rotation. So let's say we bring in our battery, attach a couple of wires to it, and let's say we directly attach these wires to our coil. Then, as the coil starts spinning, because the current starts flowing through it, you will see that the wire starts twisting and tangling and whatnot. But now, more importantly, at this position, we want the current to reverse. How do we do that? Well, we could either flip the battery or we could flip this connection. We can make this wire come here and this wire come here. Then the current direction will change, the forces will reverse, and the coil will continue to spin. But how do we make this happen automatically? That's the question, right? How do we make it automatic? Well, it can be done by using a device called a commutator. A commutator consists of split rings, which are basically two half metallic rings with some gap in between, and a couple of carbon brushes. So the wires are attached to these brushes, and these brushes are just in contact with these rings. They are not connected to them. Because of the contact, electricity starts flowing through it, and as the coil spins, notice the ring spins with them, but the brushes just stay there. So the brushes are literally brushing against the rings, maintaining the contact, and making sure the electricity flows through. This solves our problem of wires tangling and everything. But now, more importantly, let's see how this reverses the direction of the current every half a rotation. So right now, the pink ring is in contact with the positive terminal and the blue ring is in contact with the negative terminal. But notice what happens once the coil spins enough. Once the coil spins and comes to this position, now notice the pink ring has come in contact with this brush, the negative terminal of the battery, and the blue ring has come in contact with this brush, the positive terminal of the battery. So now notice, due to this commutator, automatically current will start flowing from here into this coil in the reverse direction, coming out from here into the negative terminal. And so the current direction flips, and so the forces also flip, making sure the coil continues to spin in our clockwise direction until again, notice, now again they will change contacts. Now again the pink will come in contact with the positive terminal, the blue will come in contact with the negative terminal, and as a result the current will now again flow this way, again reversing the direction of the forces. And so using a commutator, we have now achieved complete motor action. So what did we learn in this video? Well, we learned that a motor consists of a couple of magnets and a current carrying coil. The magnetic field pushes the coil, making it rotate. And the important thing is, every time our coil comes perpendicular to the magnetic field like this, we want the current to change directions. That is achieved by a commutator, which is basically two split metallic rings and a couple of carbon brushes. So changing the current changes the direction of the force and ensures that the motor keeps spinning in the same direction. And so this is how we can now convert electricity into rotation. And if we have enough current in this, and if the coil and the magnets are strong enough, then we can attach anything we want to it like a fan or washing machine, electric drilling machine, and make it spin using electricity.
Yes. So I hope this is understood. Now let's recall once again about this DC motor. Why it is called DC motor? Yes, let's see that. See here, when the direction of the current is at right angle to the direction of magnetic field, then the force experienced by the conductor is maximum. So here the force is maximum when the conductor is perpendicular to the direction of the magnetic field. Okay, in this case it works, and if the conductor is parallel to the magnetic field, then the force is zero. Force experienced by the conductor is zero. That's what it is called a DC motor. Cleared? So when the direction of the current is right angle to the direction of the magnetic field, then the force experienced by the conductor is maximum, and when the current carrying conductor is held parallel to the direction of the magnetic field, then the force exerted on it is minimum or zero. So there is no any force experienced by the conductor when the conductor is placed parallel to the direction of the magnetic field. Okay, so this is about the DC motor. Okay, now let's discuss about the question answers. First one, that is Q question answers. Consider a circular loop of wire lying on the plane of the table. Let the current pass through the loop clockwise direction and apply the right hand rule to find out the direction of the magnetic field inside and outside the loop. Okay, here the figure is given. Just observe that figure, and current is in a clockwise direction. Current is in clockwise direction, and see the direction of the magnetic field. Okay, here by applying right and thumb rule, we find that all the sections produce magnetic field downwards at all points inside the loop. So inside the loop, magnetic field is a downward direction. Then at all points inside the loop, while at the outside the points, the field is directed upwards. Okay, outside the loop, the direction of the magnetic field is upward. Therefore, the magnetic field acts normally into the plane of the paper at the points inside the loop, and normally out of the plane of the paper at points outside the loop. Next, second one, the magnetic field in a given region is uniform. Draw a diagram to represent it. So when the magnetic field lines are uniform inside the magnet, right, inside the bar magnet or inside the solenoid and bar magnet both acts as a same, right? So a uniform magnetic field in a region is represented by drawing parallel straight lines, all pointing in the same direction. For example, uniform magnetic field which exists inside a current carrying solenoid can be represented by parallel straight lines pointing from its south pole to north pole. So parallel lines are from inside the magnet moves from south to north, and outside from north to south pole. Okay, the next one, which of the following property of a proton can change while it moves freely in a magnetic field? So the magnetic field, they are if they are in concentric circles, then the proton gets velocity and momentum. Okay, it can be changed. Velocity and momentum of the proton can be changed when it moves in a magnetic field. Okay, the next one, in activity 13.7, how do we think the displacement of rod AB will affect it if current in rod AB is increased? So what happens when the current increases? The displacement also increases. Then a stronger horseshoe magnet is used. In that case also the displacement of rod AB will increases. Then the length, as the length increases, the force acting it will increases, and displacement of the rod increases. So in all the cases, the displacement will be increases. The next one, sorry, this is a positively charged particle, that is alpha particle, is projected towards west, is deflected towards north by a magnetic field. So what would be the direction of the magnetic field? If any one charged particle is projected towards west, it is deflected towards north, right? That is upward direction. Okay, the next one, state Fleming's left hand rule. This is important. This question is very important. State the Fleming's left hand rule. You stretch the thumb, forefinger, middle finger mutually perpendicular to each other. Then the first finger, that is forefinger, points in the direction of magnetic field, and the second finger means the middle finger indicates the direction of the current. Then the thumb will point in the direction of the motion or force acting on the conductor. Second question, what is the principle of an electric motor? It works based on the magnetic effect of current. A current carrying loop experiences a force and rotates when placed in a magnetic field. The direction of the rotation of the loop is given by Fleming's left hand rule. Then the last question, what is the role of split ring in electric motor? So the split ring in the electric motor act as a commutator. Okay, it is also called as commutator. Main function of commutator is reverse the direction of the current flowing through the coil after each half rotation of the coil. Due to this, the reversal of the current, the coil continues to rotate in the same direction. So copy all these questions to your notes and learn those question answers. Thank you.